Welcome to those joining us. My name's Sarah Walker. I'm our chair for the session today on grid flexibility by electrifying energy networks. And our SuperGen webinar speaker today is Dr. Zhang, who's a senior lecturer in energy systems at Cranfield University. His research experience covers power systems planning and operation with renewable energy and land-air transport electrification considerations from a grid interaction viewpoint. He's supervising 6 PhD students currently and researching as PI on projects funded by the EPSRC SuperGen Energy Networks Hub, as well as Department for Transport. He's also our SuperGen Energy Networks Chair of our Architectures Working Group and a senior member of IEEE. Dr. Zhang worked at National Grid for 8 years before joining Cranfield, and when he was there he undertook power systems planning and real-time operation work, mainly in the UK Electricity National Control Centre of National Grid UK. He's also initiated and managed several of National Grid's network innovation projects with UK universities, and he originally obtained his PhD in electrical and electronic engineering at the University of Manchester. And before I hand over to Dr. Zhang, just a couple of housekeeping things, which is if you could keep your microphones muted, please, while the speaker is talking. It just helps reduce background noise. We'll take questions in the chat function. I'll keep an eye on those, and we'll go to questions at the very end. We don't have loads of people on the call, so it could be, if we don't have lots of questions, that we'll ask each person to unmute and address their question direct. We'll just see how busy it gets. But I'll hand over now to Dr. Zhang.
Thank you very much, Sharon. Thank you everyone to come and attend this webinar event. So let me share my screen. Okay, so today I'm going to talk about a SuperGen Energy Network Hub funded project, grid flexibility by electrifying energy networks for airport. So I would like to see this is a very unique and different projects as we try to link up the aviation and power industry through a new concept of aviation to grid. So maybe it's the first time you hear this concept, and I hope you will find this project interesting. Firstly, I'd like to talk about the bit background of the project. So at the moment, the air transport sector accounts for 10% of the UK total final demand. It's still mainly driven by a fossil fuel of the aircraft and airport. To reduce carbon emission, the Flight Path 2050, the EU's vision for sustainable aviation, requires 75% reduction in CO2 emission, 95% reduction in NOx emission per passenger miles, and all the airport need to be emission-free by 2050. So this very ambitious target. Because of this, the electric aircraft is considered as one of the promising solutions because it does not emit the CO2. So at the moment, it's 200 innovation projects focused on electric aircraft globally. It's conducted by Airbus, Rolls-Royce, and NASA, and many other aviation companies, targeting a service date in next 10 or 20 years. So this is the CO2 roadmaps for global aviation. If you can see, if we're doing nothing, the air transport demand just increase together with the CO2 emission. So it's a lot of actions need to be done to reduce the CO2 to net zero by 2050. One of the key technology is the new aviation technology and sustainable aviation fuels. So electrification is considered as one of the solution. So on the ground, we have electric power networks. So electric power system is also need to meet net zero legally binding emission target by 2050 by the UK government. Because of that, is a lot of renewable energy will be or have already been integrated into the power systems. So most of renewables is considered as a power electronics interfaced, non-synchronized generation that will cause a lot of problems on challenge to the future power system. So one aspect is the frequency. So especially frequency response is required. So it's a lot of additional frequency response are required to stabilize the grid frequency in a future low inertia power systems. So this figure shows a kind of typical power system frequency control from a national grid ESO operability strategy report. So the frequency is stabilized around 50 Hertz. And when there's a sudden incident happen, the frequency could fall very quickly to a very low point beyond the operational limit. And then there's a primary frequency response and a secondary frequency response are needed to arrest the frequency from falling and restore the frequency back to the operational limit. So, and then you may think, well, one side is aviation, one side is power grid. So how these two can be connected together? So that is through the electrification because of this all new electric aircraft that will step in to the air transport industry. So I give you one example is the aviation industry requires the power grid to provide the low carbon and reliable electricity to charge their electric aircraft. At the same time, the power grid see there's additional load from the electric aircraft charging based on the factor that the power grid is already struggling with the power generation capacity, especially in the winter cold days. Power grid may already use up all the generation available. So how they can accommodate additional electric load from aircraft charging. So just give you some figures. So in aviation industry, the electric aircraft requires 200 kilowatts energy to fly 200 kilometers distance. So that is a lot of energy that is required per aircraft. And even if the first daily short-haul flight is electrified across the whole UK, which means there will be additional 1.2 to 3.6 gigawatts more electricity generation will be required from the power grid. And also the current fast chargers for the electric cars or electric buses is not quick enough to charge electric aircraft. So based on the current fast chargers, can only charge aircraft in 4 to 20 hours, which is infeasible because normally the turnaround time of aircraft in the airport operation is within 1 hour. So those are three challenges that if we connect aviation to power grid. So here we propose it's kind of a new charging process that uses battery swap process. As you can see, when a new aircraft arrive and landed to the airport, they will taxi into a terminal building, and then the empty battery will be swapped with a full battery. And then those empty batteries will be queuing in the battery swap station and then goes to a battery chargers to charge the battery. When it's got fully charged, they will swapped with another battery from another aircraft. So this is kind of the conceptual charging process that we proposed for the future airport to accommodate electric aircraft charging. So here you can see it's a battery swap station and battery chargers here. To give you a bit more details about the airport charging system design, so here's diagrams that we propose how to successfully charge those electric aircraft using the battery swap process. So in the diagram, you can see there's a PV generation, there's a gas turbine and electricity grid. So basically those are the three main electricity resources that we are going to use to provide electrical energy and power to charge the electric aircraft. But the systems can do more than that. The first concept is off-grid charging, because we don't want to add more burden to the existing electricity grid. So what we can do is we can install the on-site gas turbine and renewable energy generation technologies to provide off-grid charging to the aircraft directly. And some of charging like gas turbine can provide really super fast charging directly to the aircraft batteries. So at the same time, you can see those spared generation capacity at the airport can also provide the grid service. For example, the gas turbine can provide high power grid service and peak electricity to the power grid, where the batteries from the electric aircraft can also provide fast response grid service. So that's basically is a conceptual design of the charging systems. I want to mention that in terms of charging pattern of the electric aircraft, it's very, very different from the electric vehicle charging, because aviation is a highly scheduled industry, requires very high power charging in the short flat turnaround time. So that charging pattern is really different from the electric vehicles. So how to kind of make a charging scheme that is suitable for the electric aircraft charging is very challenging questions. So now I want to talk more about the aviation to grid perspective. So that is the concept that we proposed the first time, aviation to grid, A2G. So it's a similar concept to the V2G, electric vehicle to grid, but they have a different aspect. So, so what is aviation to grid? So we define aviation to grid is using the electric aircraft charging as a new energy source to provide grid services. So in terms of frequency response, in terms of peak shaving of the electricity demand on the power grid. So how it works? Basically, you can see this diagram. There's three blocks. So the first block here is airport operation. So for the future airport, we have PV, we have gas turbine, we have battery swap, and we have aircraft arrives and departure as managed by the airport operator, so within the airport. So in addition to meet the aviation requirement of the airport, the spare capacity of a gas turbine and charging batteries can provide additional frequency control for the power grid. So that signal will fit in the frequency control center to tell the control center how much capacity we have from airport that can be used for the frequency control and grid service. So at the same time, the bottom block is a power grid. So power grid has a full monitoring and control kind of systems, and they can forecast when the event will happen and how much the frequency response service that the grid needed. They will also fit this information to the frequency control strategy. So here, the frequency control strategy will take the requirement from power grid and a capacity available from the airport operation to decide how much power and energy the airport will be provided to the power grid. So this is kind of a new concept of aviation to grid. So now I will talk about a detailed design of the airport charging systems. The first one is solar PV. So how do we know that how much solar PV will be available for each airport? So here we do some case studies. So we take the London Gatwick Airport as examples. We calculate the kind of land space within the whole airport, and we identify different land types. So for the runway, we can't do anything on the runway. We can't put PV panels on the runway. So that is not a good idea. So runway cannot be used for the future PV installation. But for other spaces like the car park, free land, and building rooftop will be ideal place to put the PV panels. Based on those availability of land, we calculate the airport PV maximal install capacity for London Gatwick Airport and for other 7 airports in the UK. Based on 1 megawatts PV installation capacity per 5 acre of land. And then based on the global solar energy estimator model and ingredients data, we calculate how much actually PV output based on the maximal PV installation capacity for each airport. So that is the PV generation that we calculated. So the next generation within the airport is gas turbine. So this is pretty much standard modeling of the gas turbine. So we define some operational parameters of gas turbine, including efficiency, the rated power, the ramp up, ramp down rate, and minimal up and down time. So basically, the gas turbine need to operate within the maximal export limit and minimal stable limit. In order to provide frequency response service for the gas turbine, the actual operating point of gas turbine is constrained within the 30% of its rated power, so that there's additional headroom and footroom available for the gas turbine to provide operation reserve and frequency response. And also we modeled the ramp up and ramp down rate of the gas turbine, as well as the minimal up and down time of the gas turbine in the airport. So for the battery swap process, so that is maybe a bit new to you. So basically we take the business model and similar to the electric vehicles, and we did some modifications. One modification we did is we assume that all the batteries will be managed by the airport operators. Therefore, the total numbers of batteries and total numbers of charging stations are fixed per airport. So that is a modification that we made. And also we use a state flow model to model the battery swap process. So we classified 3 states of the aircraft batteries. So one state is the empty batteries that are being swapped from the aircraft and waiting for charge. Another state is the aircraft batteries that are already connected to the charger and is currently charging. And third stage is the fully charged batteries. So there's in total, all these 3 states add up together equals to the total numbers of batteries per airport. And also we simulate battery swap process as well. So the total number of batteries that required to be charged equals to the empty battery plus the battery already being connected to the charging. And also we use the state flow model to model the battery swap process. So from state 1 to state 2, so this battery is being swapped, and the battery is being swapped from aircraft to a charging station, from charging station to a charger, and from charger to the aircraft. So this diagram shows the basic energy flow within the battery swap process. As you can see, the left is is a charging battery. It's mainly use electricity from power grid and solar PV. When it's come to discharge to a power grid for the A to G, for the aviation to grid frequency response, it's mainly discharged to the power grid. So that is how the energy flow within this battery swap process. Well, we did some mathematical modelings. Now is the time to do a case study for the UK airport. So we surveyed the 50 commercial UK airport, and then we ended up with 8 busiest UK airports. So that will be the first batch of the airport to be electrified. So, so those 8 airports account for about 40 to 45% of domestic passengers across the UK. And then the next kind of case study assumption we made is we only assume domestic flight to be electrified. So we kind of ignore the international flight at the moment because we want to be realistic due to the battery energy density and range anxiety. So the all-electric aircraft cannot fly that far. So we only assume the domestic flight will be electrified. So this is a flight schedule. Maybe this is the first time you see this because most of you are kind of power and energy engineers. So this flight schedule is mainly managed by the air transport engineers. So here is summarized the flight schedule for the 8 UK airports. So we add up the how many numbers of flights on hourly basis for 24 hours a day. As you can see, from midnight to 6 a.m., so there's no flight has been scheduled. And then there's 2 peaks. One is the morning peak from 8 a.m. to 10 a.m. And another peak is evening peak from 1800 to 2200. So there's 2 peaks of flight schedule. Once we got this data and based on our mathematical modeling, we can decide the generation capacities within this 8 UK airports. So for example, the PV generation capacity based on the land availability has been calculated across the 8 airports together with gas turbine, the size of gas turbine, and number of batteries and number of battery chargers. So those are fixed per airport, but different across 2 different airports. Here you see the grid. So this grid is grid transformer that connects the airport to the main distribution network. Because we cannot make a standalone airport system, we have to connect the airport to the external grid just in case if the emergency happens, we still have a grid electricity to supply the airport. So the size of grid is assumed to be the same as the gas turbine size within the airport. So why we make this assumption? Because it's considered as N-1 reliability criteria. So if a gas turbine falling down or have outage, we still have the same amount of power that we can get from the power grid. We also made some assumptions for the electric aircraft. So this time we use a hybrid electric aircraft that use combination of traditional fuel and batteries for the aircraft propulsion. So a similar idea as a hybrid electric cars, partially use the conventional energy and partially use electric energy. So I want to draw your attention that the battery size here, the battery energy density, the battery energy capacity is 23 megawatts hour. So that is very, very large battery compared to the electric buses and electric cars. So we've got mathematical modeling, we got case studies, we got the assumptions. Now is the energy dispatch result within the airport charging systems. So I want to give you some figure first. So based on our calculation, we assumed that daily energy consumption for the electric aircraft charging across this 8 UK airports is 8 gigawatt hour. And within this 8 gigawatt hours, half of them are met by the off-grid charging, like the gas turbine on site, and 20% of them met by the renewable energy charging, like the PV solar panel installed in the airport. And actually, the energy dispatch strategy can meet the flight schedule requirement, can fully charge the electric aircraft within 15 minutes. So now we look at the detailed energy dispatch kind of result for the 24 hours a day in a typical airport. So you can see here, the negative value here is actually is a demand. So it's a charging demand by the electric aircraft. And then the top is a generation, is try to meet this demand on hourly basis. As you can see, from midnight to about 7 a.m. in the early morning, so all the charging demand will be met by the power grid. Why? Because the electricity price is very low during the night. So that's why for our energy dispatch strategy, we buy all the electricity from the power grid for the electric aircraft charging. And during the daytime, because the grid is also maybe full capacity already, so we use the gas turbine, on-site gas turbine within the airport to meet the electric charging demand. And also we allowed maximal kind of PV generation during the daytime as a part of renewable energy for the electric aircraft charging. So the last point I want to make here is if you look at the charging demand we propose for the electric aircraft, that will be different from the actually national power demand of a power system. For example, during the night, it's a demand valley for the national grid power system. But here, we have a lot of electric aircraft charging that can fill that valley, whereas during the daytime, we do not need any electricity from power grid. Instead, we use on-site gas turbines. So that could be complementary to the national grid demand profile. So now I give you more details about the aviation to grid frequency response services that we calculated. Basically, the two energy resources, one is gas turbine, one is electric aircraft batteries. So how we use up these two to provide frequency response service. So for the batteries, so we assumed the batteries at the moment connect to a charger, and a charging at the moment can provide primary frequency response. So all the fully charged batteries, which is in the battery swap station, cannot provide frequency response because they do not have a cable to connect to the network. So only the battery currently are charging can provide the frequency response. The way to provide frequency response is when the grid has some emergency situation, they will send a signal to the airport. So the airport will stop all the electric aircraft charging, but at the same time, to start discharging those batteries back to the power grid. So that will provide double volume of the charging power to the grid. And as you can see, batteries respond fairly quick. So that can be used for primary frequency response and being required to sustain for more than 30 seconds and then gradually reduce their output because we want to avoid the second sudden imbalance. So the battery will gradually reduce their output. At the same time, the gas turbine can also provide primary and secondary frequency response. It's slower than electric aircraft batteries, but can sustain longer for more than 30 minutes. So that is perfect with energy sources for the secondary frequency response. And now you can see all the gas turbines and electric aircraft which are available can be discharged to power grid if the power grid has event. So that shows how effective the A2G as additional frequency response service can save the frequency from falling compared to the red curve, which is the frequency deviation without A2G. And here it shows the frequency response power. So the volume of the frequency response capacities that gas turbine and electric aircraft battery can provide. As you can see overnight, for the 8 UK airport, it can provide about 1,200 megawatts response power to the power grid. And during the daytime, because of busy flight schedule, most of power will meet the aviation requirement first. So only half or 1/3 of them can be used as a frequency response. And also mainly the response power are provided by battery, because battery has, flexibilities to quickly provide the frequency response power. When we come across response energy, so this time it's a gas turbine. The brown curve shows gas turbine can provide much higher than response energy than the battery. That is because the gas turbine can sustain longer, up to 30 minutes, compared to the battery only can sustain 30 seconds. So this is a whole kind of A2G frequency response service. The volume, the capacity, and the time scales that the airport charging system can provide to the power grid. So here I talk about more details about the A2G, aviation to grid frequency control. So we test different scenarios of the power system operation. So here we use the GB power system models. So we model all the responsive synchronized machine on the power system. We also the generation losses, which is 1800 megawatts. We model the system inertia. Most importantly, we model this novel A2G frequency response control from the airport. So as you can see, part of the frequency response control are provided by the gas turbine, and part of them are provided by the electric aircraft batteries. And I just take 4 classic kind of examples for the different period of day and for the different season, how the frequency deviation can be improved by the A2G frequency response service from the airport. You can see for the summer morning, because there's summertime, so not many generators are running on the system, and system inertia is low. So when the night 1800 megawatts loss happened, have a huge frequency drops, where the A2G frequency response can save the frequency from falling and able to pulling back the frequency, restore the frequency back to the operational limits, which is above 92.8 hertz. For all the scenarios, the A2G will kind of provide additional support for the frequency deviation. And the least effective case is a winter evening, where the grid is already strong with a lot of synchronized machines on the system. For that situation, the A2G frequency response from the airport is not needed. So I'm talking about a lot of technologies and figures and calculation, and it shows that, well, it's a fantastic technology. So let's do it. Before that, we need to also look at the commercial perspective in terms of charging cost and revenue. So how much this airport charging system will cost. So here we use the optimization functions to focus on the operational cost of this airport charging system. So mainly focus on the amount of electricity. Oh, sorry. It's mainly focused on the electricity price that we buy the electricity from power grid. It's also part of the gas price that we buy from external gas grid to power the gas turbine on site of airport, and also offset by the A2G frequency response revenue, because for every 1 megawatt hour frequency response service that we provide to the grid will pay about £10 per megawatt hour for every 30 minutes to the airport to buy this frequency response service. And based on the calculation, so we list about 8 airports, the charging costs and revenue. So the first of charging cost across the 8 UK airports can be as high as 230 million. So that is a fuel cost combined with electricity and gas kind of cost to charge those electric aircraft. And also the charging costs are well balanced between the electricity and gas cost. Is about half and half. So half cost will be provided by electricity, half cost will be provided by the gas turbine. And also the frequency response revenue, that is additional revenue for the airport paid by Power Grid, is 45 million. So as you can see, the frequency response revenue can offset a certain percentage of the total charging cost within the 8 UK airport. So just give you a summary of these project outcomes. The frequency response through the electric aircraft charging as a new energy sources. So this is a whole concept of the A2G, Aviation to Grid, that we proposed in this project. And we have done the case study of the 8 major UK airports, with about half of the domestic electric aircraft will be electrified by 2030. So we find out this 8 GWh additional daily energy consumption is required for electric aircraft charging. The total A2G frequency response service can reach about 800 megawatts during the day and 1400 megawatts overnight. So it's a very large volume of the frequency response service can be provided to the power grid. And the annual A2G charging cost as high as 230 million, and about 20% of this cost can be recovered by the frequency response revenue from the power grid to the airport. So just a couple of future thoughts on this novel kind of topics to link up the aviation with power grid. So far we talk about battery swap. So how about direct charging? How about different charging arrangement that we put a very high power charging directly to the aircraft and use some energy battery storage to balance the charging between the PV electricity grid and aircraft demand. So that could be also options to look at in the future by using direct charging rather than battery swap. But we feel that direct charging requires a lot of high power chargers, which is unavailable at the moment. Another thought is kind of multi-skill integration. So electric air transport is considered another energy network in the air that also transport energy from one airport to another airport. Actually, all these airports can be mapped into the electricity power networks. Depends on the location of airport. So this electric air transport system can also provide additional kind of support to power grid, not only the frequency control, but also potentially constraints management, because those airports are spread out to different locations of electricity power network. If we can control the charging demand of each airport, we may be able to find another way to manage the constraints, system constraints, not only a frequency, but also voltage, thermal constraints, and even the fault level on the system. So this is the last slide I'm going to talk about, is a publication and future funding based on the Supergen Energy Network Hub's flexible funding support. So far, we have 2 applied energy papers. One is in third revision, is Aviation to Grid Flexibility, which is talking about this novel concept. So it's in the third revision now. And another paper is to design the airport as a microgrid energy system using the concept, as I mentioned before, that is already been published on applied energy. And we also did a presentation in a recent international conference on applied energy to talk about the aviation to grid. So for the future fundings, So the Department for Transport is also very interested in these ideas. So they fund us a project through their Technology Research Innovation Grant to specifically looking at the hybrid and smart charging infrastructure for the electric aircraft. And also we got another EPSSC Doctor Training Partnership project from the EPSSC. So I also would like to kind of thank you for my PhD student, Mr. Zekun Guo, who is full-time working on this A2G Aviation to Grid project, partially sponsored by Cranfield University on this Supergene Energy Networks project. So if you have any questions, you can feel free to contact me through these two email addresses below. So this is all I've got for today. Thank you very much for listening and attending this presentation. Thank you very much.
That's great, thank you. We've got a comment in the chat from Paul. Paul, would you like to unmute yourself and raise this point?
Hi, yes. Jen, very interesting. Thank you. Very clear. Very well put. So I'm wondering if the main driver for electrifying aircraft is essentially to reduce carbon emissions from the airline transport industry, then how does the use of a gas turbine sort of affect that carbon reduction? And I mean, what would you envisage actually powering it? Would it be hydrogen or natural gas or what? Or is that, I mean, I would have thought that the life cycle of the carbon would actually be increased by using a gas turbine to charge a battery to run on an airplane because of the weights involved, but maybe I'm wrong.
You are right. It's a very good question. Actually, I think our initial approach is to use gas turbine because it's established models for gas turbine. But in the future, we'll consider hydrogen as a decarbonized fuel. So the hydrogen fuel cell generator will be a technology to replace the conventional gas turbine plant. That will kind of reduce the whole carbon cycle across the aviation and power grid. So that is a kind of future work that we are going to do. So gas turbine is only a starting point because we're looking at the long way by 2050. So the hydrogen would be the solution that we are going to use in the future to replace the gas turbine.
Right. And the other thing that very quickly that struck me was that surely the cost of batteries is much higher than the cost of chargers in general. And yeah, wouldn't you want to use as many chargers as you had, as you could really to charge the batteries as slowly as possible rather than actually physically moving them, so you'd have a charging station at every stand?
Yes, you are right. So that is part of the infrastructure cost. It's also need to be considered because at the moment we only consider operational cost. So when we come across infrastructure cost, there will be a trade-off between the charger infrastructure cost and battery cost. Actually, we did an initial assessment in our international conference Apply Energy papers to look at different charging options. And we found out for some airports, they reduce the number of batteries and invest more charger would be an ideal option. For other airports, maybe battery swap will be the option. Yeah, but you are right. The infrastructure cost is also plays a big part in this airport energy system design.
Okay, thank you.
Thank you.
Thanks for those questions, Paul. We've also got a question in the chat from a user named SCAV. Do you want to unmute and raise this question?
Yes, hi. It comes off as SCAV, but that's not my name. My name is Lai from Warwick University.
Hi.
You don't know how to change that. Anyway. Yeah, so I was saying that assuming battery swapping assumes that there's some uniform standard in where planes are designed where there's easy access to install the battery and to remove it. This was discussed for electric vehicles, but EV manufacturers could not agree on a uniform standard, and two, from the perspective of power electronics and maximizing, energy density, so on and so forth, it just wouldn't work. So how realistic is this assumption that you're just going to be able to park your plane, remove your battery, and put in a new one?
Yeah, you are right. So this is this research is still at early stage. I think the battery swap, especially different types of aircraft, may have different batteries. So this is kind of common problems for the electric aircraft. So we didn't consider this challenge in this research. So what we considered is a number of batteries. For example, for the big aircraft, we assume 50 batteries pack, while for the smaller aircraft, we assume 10 battery packs. But we assume all the batteries are identical. But in the reality, I think it's important for the aircraft manufacturers to standardize their kind of batteries. Because even for the electric aircraft, it's still at early stage for design. So they have the next 20 years to standardize the battery design for the electric aircraft. So I think this project could flag up those information to the aviation expert or manufacturers to say how important it is to standardize the swappable batteries. Not like the EV. It's maybe already too late for the EV.
Just one more quick comment. Every time I hear people talking about hydrogen, it always confuses me because, I mean, for me, hydrogen only makes sense if there's some free source of it, if it's not coming from electricity. If it's coming from electricity, that means you need electrolysis, you convert it to hydrogen, then you convert it back to electricity, and the round trip efficiency of that is very low.
Yeah.
So the answer to your previous question about the use of hydrogen, it just never really makes sense to me. Maybe there's something I'm missing.
Yeah, so I think really good questions. So I think in our future work, we consider two kind of potential resources to produce hydrogen. The first one is we assume electrolyzers. So the PV or renewable energy, or even the cheap electricity from grid can be converted to the hydrogen through the electrolyzer. So the second options would be the hydrogen from external transport, like they have hydrogen valley somewhere and then transport hydrogen in. So again, the hydrogen supply chain issues is maybe another research that need to be addressed as well. But again, there's a bit uncertainty on that. So for us, we only focus on the energy system design within the airport, as well as the grid interconnection. We haven't kind of researched too much on the hydrogen supply side. But you are right, so this is an issue that we are aware. Yeah.
Great, and we have a question from Katie on solar energy charging. Katie, do you want to address that?
Yeah, I mean, sorry if you've already covered it in the beginning of your slides. I came in a bit late. But yeah, just to ask a bit more about if solar energy charging was an option. And it sounds like, so if you have batteries, but you also have, say, hydrogen or gas or something, then you kind of have two forms of energy storage. But you could actually take quite a lot of advantage of having these movable batteries because they can be, you can charge up when you've got excess solar or excess other renewables, and then hopefully store them or something, I guess. Just your thoughts on that.
Yes, I completely agree with you. So in our latest applied energy paper that's been published, it's a microgrid airport systems. We use both hydrogen and grid electricity. And within that microgrid airport systems, we use two forms of storage. One is hydrogen storage, one is battery storage. And we kind of optimize operation between these two energy storage facilities. So if you are interested, you could have a look at the paper. So I think that would be kind of reviewers from those publications. They think we need to keep the option open. So they cannot only use one hydrogen or purely electricity from grid. So we have to make multiple options for the future. So that paper is talking about.
Yeah, no, I think that makes sense. So you can have some short-term storage and long-term storage and things like that. Yeah. Thanks.
Thank you.
Great. And another comment from Paul around EV parking.
Yeah, sorry, I don't want to hog questions, but I'm just had a thought that, you know, car parks, you mentioned car parks before and how you could put solar panels over them probably.
Yeah.
Don't the car, if there are a lot of EVs that are sort of left basically for a known amount of time in the car park at the airport, you know, the airport car parks tend to be quite large. Ultimately, most of those cars will be electric, battery electric. Surely that's a big resource actually in terms of batteries just parked there doing nothing. That could presumably also be used for flexibility, perhaps.
Yes, it's really good ideas. Yeah, so the use electric cars parked in the airport car park can also be considered as a part of the A2G, especially, you know, I agree with you, especially we know when the people are going to park their car for how long and when they are coming back based on the flight tickets they've got. So actually, it's quite easy to manage those electric vehicles in the airport car park. So I agree with you. I think in the future, we will definitely include the airport car park electric cars. It's a really good idea. Thank you, Paul.
So I mean, I know with the Heathrow expansion sort of consultation, one of the big carbon emissions from the airport was in fact the ground transportation associated with it. And obviously that I did one of my comments to them was that, yeah, just make sure the electricity connection for any expansion is big enough to accommodate all of that. I didn't ever see actually their plans for, you know, the size of the grid connection that they would need. Because it seems to me that, you know, if you plan this in early enough, a big grid connection really isn't a problem, especially if you can be flexible about the time of use. I mean, presumably there's also a lot of ground vehicles, you know, the tugs and the buses and things that are needed in the airport that could also be electrified or would be electrified.
Yes, I think recently we've been talking about some substation construction companies. They all said that the grid connection is very expensive if you want to build up new cables between the airport to distribution networks. So that's why we think about off-grid generation options, like to install the local solar farms, local generators to at least to half the grid supply requirement from the power grid. So yeah, but you are right. So we need both, you know, grid connection as well as the off-grid generation option. Yeah, so we keep both options open.
Thank you.
Yeah, thank you.
Great, we've got time for one more question, and that's Dar. Would you like to unmute and address this?
Yeah, thanks, Sarah. Thank you, Dr. Zhang, for the presentation. That's very interesting. So my question is, because the battery seems to provide a lot of services, including frequency response and charging the aircraft. So my question is that since the battery will be charged and discharged very frequently, will this cause fast degradation? And what will be the lifetime of the batteries used for aircraft?
Yeah, that is really good questions. So I think first of all, we consider the frequency response service is like the insurance. So it won't happen very often, but if it does happen, so something bad happened on the power grid, the service will be there available to save the frequency and save the blackout. So that event is rarely happened. Maybe you heard recently the taxis in the US, they have a power blackout because of very cold weather. That's on media everywhere. And also back to the UK, 2019 lightning strike caused the power blackout. But those blackout event is kind of a rare event. So in the reality, maybe the airport, they provide this response service available to the grid, but maybe the grid never use it. Just in emergency, they need to make available. So it's like an insurance concept. Once it's made available, the grid will need to pay the airport the response cost. So that wouldn't impact too much on the aircraft battery degradation, we hope. And secondly, if the event happened, the battery only required to discharge back to grid by 30 seconds. So that wouldn't impact the, by 13 seconds, it's only, based on our calculation, it's only use up like 10% or 5% of a battery's total capacity. So that wouldn't impact the whole aviation operation. You know what I mean? Yeah. So yeah. So this is our consideration. Thank you.
Yeah, thanks. That's very helpful. So do you know what will be the lifetime of the batteries to be used for this kind of aircraft?
So we did some life cycle analysis in our Microgrid airport papers for applied energy. So normally the batteries, so we assumed the life cycle is around 10 to 15 years.
Okay.
So if you talk about the 25 years project period, so the battery need to be replaced by twice or 3 times. Where the hydrogen fuel cell generator is only 5 years, so that need to be replaced many times. So yeah, so that is yeah, but I'm not a battery expert, to be honest. So that's why I think our energy system design need to keep tracking the latest battery technologies and to make modifications on our energy networks. So that is yeah, that is my consideration.
Yeah, I see. Yeah, that's very helpful. Thanks.
Thank you.
Great. Well, we're just about out of time. Thanks everybody for taking part, and thank you so much to our presenter. The session has been recorded and will go up on the Supergen Energy Networks Hub website in due course, and we'll send round, no doubt on Twitter, a link to that so that you can share that with people who couldn't quite make it today. But thank you so much to our speaker and to everybody for getting involved and dialing in. Thank you.
Thank you very much. Thank you, everyone.
Thanks. Bye-bye.
Bye.